So we continue with the same example in which the velocity field is given to us in a two-dimensional situation where the component u and y and u and v of the velocity are as given as indicated in the velocity vector in two-dimensional motion. I, j are unit vectors in x and y respectively, and this time by using the formula for material derivative we try to calculate acceleration field and its relevant component. So you can see, since the x component of acceleration is partial derivative of du by dt plus u into partial derivative du dx plus v into partial derivative of u with respect to y, and similarly partial derivative of u with respect to u. This is the formula or the components for acceleration component in x direction. Similarly, there will be components for y, there will be components for z. The components in the z direction in this case will be 0, and the only non-zero terms that we will have are likely to occur in x and y direction. And therefore, when we calculate it according to the formula, then since the velocity vector does not have any t involved there, as you see, therefore the partial derivative of du by dt is 0, but u into du by dx is what we calculate and given here as it is, and similarly the partial derivative for v into du by dy. You can see there is no y in u, there is only x occurring there, and therefore the derivative of u with respect to y will be 0, and that will reduce this term to 0, and the only non-zero contribution in this component is coming from here, that is equivalent to this. Similarly, when we try to calculate acceleration component in the y direction, then we will take the acceleration in y direction, and therefore now the we shall be differentiating things with respect to small v, which is velocity component in the y direction. dv by dt, partial dv by dt is 0 because no t occurring in the v component. U dv by dx, again, since there is no y in the v component, therefore the contribution from there, the partial derivative dv by dx will be 0, and when it is 0, the whole term will be reduced to 0. The only non-zero term in this case is coming from here. We substitute the relevant value, and this is what we obtain. And then, so what is the acceleration field? The acceleration field will depend on this component for x and this component for y, and therefore at a given value of x and y, for example, let us say at x equal to 2 meters and y equal to 3 meters, ax, the acceleration in x direction will be 1.68 meters per second square, and the acceleration in y direction will be 0.72 meters per second square. And similarly, these equations can be involved to the other components also. And then we try to draw a flow field. These values that you have seen given here in pink are for a specific point where x is equal to 2 meters, y is equal to 3 meters. As we vary these numbers, as we take the whole flow field, let's say in x, y and in a plane, then we will see that the flow field, the acceleration field, will be looking like this. The acceleration over a scale of, the length is being shown as 10 meters per second square. This is just an arbitrary scale. You can increase or decrease as you like, but it just shows how the fluid is moving across in different directions and how it will be changing, how the fluid will be flowing. And note, as before we have pointed out in the earlier part of calculating this exercise, discussing this same example that we were, the stagnation point at 0 exists, and therefore the velocity and the acceleration both are 0 there. So this is how the field. And similarly, for different values, for different exercises, for different velocity fields, we can compute these values in all those cases.